All right, so final thing I want to talk about before the quiz tomorrow is electric field lines and equipotential surfaces. So you should definitely know, you should be familiar with these upper two boxes here, right? Oops. Oops. So these two diagrams here should be super familiar. So look at electric field lines. What they tell us is the direction that a small positive charge wants to move when placed in the field. And all these charges that are here, all these guys here, are these big dudes or little dudes? All the charges you see on the screen here, big dudes or little dudes? They're big dudes because they're creating the field. Now, if you stick a little positive guy, so let's start with the easy situations. If you put a little positive guy right there, which way is that little positive guy going to go? He's going to go that way, and that's the direction of the electric field. What if you stick a little positive guy right here? He's going to go that way. That's the direction of the electric field. Same thing for a big negative. If you stick a little positive guy right here, which way is he going to go? That way. The direction of the electric field is the direction of force on a little positive guy. All right, so a more complicated situation. So this is what I wanted to show you. What if you have two big guys, 2 point charges that are in the same vicinity? So for example, big positive and big negative. The electric field line between those two charges would look like this, right? And all this means is if you stick a little positive guy right there, what's that little positive guy going to do? That little positive guy is going to go up, and then he's going to get sucked in to the big negative. So these arrows that you see between the charges, the electric field lines, it's what a little positive guy would do when placed in the field. Easy enough? And then look, which way is the force? Which way is the force on a little positive charge right here in the field? How would you figure out the direction of the force on a little positive guy right here in the field? The direction of the force would be how? Would it be like that? No, it's going to be tangent to the electric field line. So a little positive guy right here, which way is the force? That way. You know, it's tangent to the field line, okay? Which way would the force on a little negative guy be? So now let's say that this dot right here represents a negative charge in the field. Well, what do we know about negative charges? Just go back to the easy situation. If you put a little negative guy right there, what's the little negative guy going to do? Goes opposite the field. Little negatives experience a force opposite the electric field. Okay? Thank you. Okay, so back to the question. A little negative charge right here, the direction of the force would be like that, right? Okay, now, how about this? What if your two big guys are both the same charge? Well, your electric field lines would look like this. You know, so if you put a little positive guy right here, is the little positive guy going to bolt across to the big positive? Because a little positive is going to be repelled by both of the big guys. So what would this little positive charge do? This little positive guy would go up like that. What if you stuck him right here? He'd go like that. So just be aware, these electric field lines show you what a little positive guy would do. Hey, what's the electric field at point C right in the middle? What would be the total electric field at point C? 0. And you want to know why that makes sense? Because if you think about it, if you stuck a little positive charge directly between these two big guys, so that dot represents a positive guy, what would be happening to that guy? Well, there'd be a force that way, and there'd be a force that way, right? And what would those two forces do? They would cancel. So therefore, there's no electric field there. If there's no force, there's no field. Does that make sense? Okay. What if these guys here, instead of being both positive, what if these guys were negative? How would that change the situation if both of these were negative? It'd be the exact same diagram, but all these arrows would point which way? In. It'd be the exact same thing, but instead of the electric field going outward, if those two guys were, if these two charges were big negative, the electric field lines would be going inward. Okay? All right, equipotential surfaces. Okay, so on Friday we talked about the idea of an equipotential surface. So here's the idea. So if you have a big guy, so this, let's look at the easy situation. You got this big charge Q. If you travel a distance r from that big charge, you can calculate the electric potential at that point. The equation for this is KQ over R. So look, if you go to another point, same distance, right? R and R. What would be true, or what would we find out about the electric potential at that point? Same thing. So the idea here is every point on this circle, every point on the circle is at the same electric potential. So we call it an equipotential surface. So when you see these dotted circles, dot, 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 like that, it's telling you that every point on there is at the same electric potential. Now, how are you going to see this in a problem? The way you're going to see it in a problem is these points are going to be labeled. It's going to be like here, let's say, is just going to make up some numbers. Let's say this is 80 volts, this is 50 volts, and then out here is, I don't know, 30 volts, okay? Notice it's getting smaller as you move away. As the R gets bigger, volts go down. So then the question could be something about moving a charge from, say, here to there. If the charge moves from there to there, what's going to be the important thing about those 2 points? The change between those 2 points is what? Well, let's see. We start at 80 and we end at 30. What's the change? Negative 50, right? If you went the other way, if you went from there to there, then the change would be positive 50, okay? So that's how you're going to use equipotential surfaces. You'll be given the potential on that surface, and then you can figure out the change. Change is what's important. Now, a couple more things, and then I'm done. I want you to notice something. Notice that the electric field lines, that's these guys, notice that the electric field line is always perpendicular to the equipotential surface. See right here? Perpendicular, 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 right? And that's going to be important when you have a more complicated situation like this. Okay, so let's look at this. So for starters, and I've seen this question many, 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 many times on a multiple choice test, looking at this diagram, which of these two charges here is positive and which is negative? So we have left charge and right charge. Which one must be the positive charge? The left, and then the right is the negative charge. The way I know that is by looking at the electric field lines. You look at the electric field lines and they're going out from here and then they end up there. So how do electric fields behave? Well, they start at positive charge and end at negative charge. So we figured that out. Now, all this is showing you, the electric field lines. So ignore the equipotential surfaces for a moment. If you stuck a little positive guy right here, what's he going to do? He's going to go like that, right? He follows the electric field line. Okay? Now, the equipotential surfaces, notice that they're not perfectly circular because it's a more complicated situation. They're more like oval shaped. But the way to understand it is that the electric field has to be perpendicular to the equipotential surface. See that? And that's why it ends up being this oval shape. See how it's not circular anymore? But the questions would be the same. The type of question you would get, it'd be like, let's say that this is 70 volts and then out here is 20 volts, right? The important thing is you would go, all right, every point on this oval is at 70, every point on that oval is at 20, so the important thing about 70 and 20 is that the change is 50. Does that make sense? So just so you're familiar with these diagrams. Huh? Well, no, like what I could ask you on the quiz is like how much work would be required to move a charge from here to there? And I'd have to give you what the charge is, and then you would use delta V as change of potential energy per charge. The change of potential energy is equal to the work. Well, bam. Okay. Any questions on this?